Hey everyone, I hope you're doing well in such unprecedented times and staying safe in your home. I'm Manish. I'm a PhD candidate at the College of Information and Computer Sciences at UMass Amherst. I work with Professor Yuri Brun in the area of software engineering and more specifically in the area of automatic program repair. I had planned to give this talk during your regular class time, but instead of making you to sit at a fixed time and view the live lecture, I decided to make it more flexible for you so that you can watch this talk at your convenience, hopefully by this Thursday, and then ask me any questions you have or just share your comments. Finally, before I begin, I would like to thank Heather for giving me this opportunity to talk about my work, and I hope that you enjoy the talk. Let's get started. So as the title of the talk suggests, I'm going to talk about automated program repair, but I'll focus on the quality of the repairs that are produced by these techniques. I'll present to you a bird's eye view of the automated program repair process, and I will talk about the key concepts briefly instead of going deep into a single concept. By the end of this talk, you should be able to tell why we should care about automating bug repairs. You should know how automatic program repair techniques work in general and the current open challenges researchers who are working in this field face. I'm sure almost all of you can relate yourself to this cartoon strip. You must have faced this situation while working on some coding assignment or some project. And this situation is not only faced by students like yourself, but it is also faced by the developers and programmers who work in the real industrial settings. Adding to the frustration of not being able to fix a bug is the frequent deadline and the complex libraries and APIs that are used the software being developed. Now the question to be asked is, do software bugs affect only software developers and computer science students like yourself? So to answer that question, a recent study was performed by researchers in which they considered the effect of 606 software failures from around 1200 news stories related to 314 companies, and they found that these software failures cost 1.7 trillion US dollars, affecting half the world population with an accumulated downtime of 268 years. So to answer the question, do software defects affect only programmers? The answer is no. As most of our daily life activities have changed significantly in the past few decades because of the advancements in the technology, software is now everywhere, your cars, your home devices, using web applications for e-commerce, booking flight tickets, and you just name it. So therefore, software defects now have a huge impact. Analyzing the cause of software failures, it was found that the current approach of software testing, debugging, and fixing defects has not improved as compared to the software development processes themselves. It's found that even today, most of the time developers do these activities manually, even in the real industry settings. To address this issue, automated program repair research area has started around a decade ago, and it involves creating tools that can fix defects in programs with minimal or no human intervention at all. These techniques can help reduce the loss and increase developers' productivity. Recently, industries such as Facebook have started to adopt these techniques in their production. Since the beginning of the program repair research area, the number of publications in this field has grown by an order of magnitude. Currently, there are at least 40 plus repair techniques and 10 plus defect benchmarks that are used to evaluate these repair techniques. All this progress indicates that researchers are actively working on to improve the state of the art. Now, while all this is encouraging, the question is, even though we have so many tools available, why is it that the developers are doing manual debugging and manual bug fixing? In other words, why these techniques are not being used in practice at a large scale. Now, to understand the real problem, we need to understand a bit more about the automated program repair process. So let's try to do that. Now, a typical program repair technique takes as input a buggy program that fails some tests and outputs a modified program, which is also called the patch program that passes all the tests. Isn't this pretty cool? Now let's try to understand what's happening under the hood. Whether manual or automated, program repair process involves three high-level steps. So given a buggy program that fails certain tests and passes other tests, the first step you need to do is to identify the program elements that are causing the bug. Now by program element, it could be a program statement or a class or a method, and this step is called fault localization. The second step involves identifying how to modify the buggy program elements that have been identified using fault localization such that it fixes the bug. Since there are multiple ways in which you can modify the buggy program elements so as to fix the bug, therefore there can be more than one candidate patches that are possible and which could fix the bug. Finally, once you have multiple candidate patches, you need to apply that patch or the modification to the buggy program and then validate the patch program against the test suite. This step is called patch validation, and in case of automatic program repair, patch generation and patch validation are fully automated steps, and they go iteratively until the repair technique finds a patch that actually fixes the bug, or in other words passes all the tests, or a timeout occurs, or you run out of all possible candidate patches and then you are simply unable to repair the bug. Now let's try to understand each of these steps in a bit more detail and how these things are done in an automated manner. So let's first start with the fault localization. So fault localization is defined as automatically determining program elements such as statements or methods that are defective and cause software failures. Now, depending upon what technique you use to determine the faulty element, you have different kinds of fault localization techniques. Also, just to be clear, I'm using the words fault, defect, error, bug synonymously. So for the purpose of this talk, it is okay to assume that all of these things mean the same. Okay. So now the first class of fault localization technique is called spectrum-based fault localization. These techniques only consider the test suite, which has the passing and failing tests, to localize the bug in the source code. So how do they work? For example, suppose you have a source program which has n statements and a test suite which has, let's say, n tests, some of which pass and some of which fail. Now, in order to understand how likely it is that the code statement I is buggy, what these techniques do is they count the number of tests that execute statement I which are passing and the number of tests which execute statement I which are failing. And then the suspiciousness score, or the likelihood that the code statement I is buggy, is determined based on a function of the total number of passing tests which execute statement I and the total number of failing tests which execute statement I. Now, depending upon what function is used, you have different types of spectrum-based for localization techniques. So for example, D-star, tarantula, Pochkai. So they use different formulas. So I'm not going to go deep into those techniques, but these all fall under the category of spectrum-based for localization. The next class of technique is called mutation-based for localization technique. Here the idea is to understand the effect of program element on passing and failing tests. So this is kind of a reverse of what spectrum-based for localization techniques do. Let's try to understand this using an example. So for example, we are given a same setup. Now, instead of trying to identify how many tests pass and how many tests fail by executing a code statement I, in this case what you're trying to do is, if you try to mutate a code statement I, so let's say for example you change the statement a equal to a plus 1 to a equal to a minus 1. So this minor modification is formally known as mutation, and then see how the test suite or the test output changes. And depending upon how many tests pass and how many tests fail, when you mutate a code statement I, that is used to determine the suspiciousness score or the likelihood for that statement to be buggy. So for example, in this case, the suspiciousness score of code statement I is a function of total number of passing tests and the total number of failing tests. So here we are not considered about only the tests that execute that statement. Here we are considering all the tests that pass and all the tests that fail when you modify a statement I. Okay. The next class of technique is called program slicing for localization. Now these techniques do slice a program or reduce a program to a minimal form such that it still maintains a given behavior that is exhibited using test suite. So for example, again suppose we have the same setup where we have a source program and a test suite. What these techniques they try to do is they try to get rid of the source code by slicing out the parts of the code such that the test suite output remains same. So this indicates that the part that is removed from the source code program are not responsible for the tests that are failing. Okay, this is called program slicing for localization. The next class of techniques is called stack trace for localization. Now, if you observe your compilation error or the stack trace that is thrown by your compilers, whether it's an IDE or terminal, it gives you a sequence of the method calls that occurred when a particular exception or a bug was found, or your program crashed basically. So stack trace based for localization techniques use stack frames. Now stack frame is slightly different from stack trace. Stack trace gives you a sequence of method calls that were executed when a crash occurred or when a bug was encountered. Stack frame is what are the frames that are added to the heap when a particular method call was active during the bug occurs. So it goes a little deep into the stack in each method and figure out what parts of the method were active when a particular crash occurred. So it uses that information to determine which program elements could be buggy. The next class for localization technique is called predicate switching for localization. Now these types of techniques are mostly used to determine the bugs in the conditional statements like if then else or switch statements. And the way they work is kind of similar to the mutation based for localization, but here instead of changing the whole statement, these techniques mutate the condition inside the conditional statements. For example, if I have a source program that has if condition, else condition, and so on and so forth, so I can change, for example, if the condition is if a minus b is greater than 0, it mutates that to if a minus b is less than 0. And then and it then tries to understand how it affects the behavior that is exhibited by the program in terms of how many tests now pass and how many tests fail. And this thing tells us what is the effect of a condition on the failing test and the passing test. And that information is used to compute the suspiciousness score for a condition I. Okay. Finally, you have another class of techniques called IR-based fault localization or information retrieval-based fault localization. These class of techniques, they use bug reports which are filed by users for the errors that are encountered in the software. So these techniques work similar to like your search engines. So these techniques use the bug report, the text in the bug report as a query, and your source code program as relevant documents, and it tries to rank those documents based on the similarity between the query and the terms that are found in the program. And there are many techniques that use different kinds of similarity metrics and different kinds of pre-processing to make sure that your bug query is able to rank the most relevant source code documents at a higher level. Okay, so other than these fault localization techniques, there are a class of techniques called fault prediction techniques that use code proneness. By proneness, I mean code complexity or its likelihood to be buggy, and the development history, where, for example, let's say there is a piece of code or a file that has been modified constantly over a period of time. So the fault prediction techniques use these factors to predict what program elements are likely to be buggy. Now, the question is, why do we have so many different kinds of techniques and what's the use? And the answer to that is none of these class of techniques is the best technique. So it's not the case that one technique will always work better than the other. And they seem to work better on different kinds of applications depending upon the different kinds of languages, projects, and so on and so forth. Now, automated program repair techniques typically use spectrum-based fault localization. Now, there are two reasons why automatic program repair techniques typically use spectrum-based fault localization. First, since spectrum-based fault localization works using test suites, so it is easier for program repair techniques to work with such fault localization techniques because program repair techniques also take test suites as input. And the second reason is that the test suites are readily available for all software. Sometimes it is hard to get bug reports or like stack traces, but then test suites are almost always available for all tests. Coming back to the program repair process, let's talk about the second step, which is the patch generation step. Now, patch generation involves identifying how can we modify the buggy program elements such that it fixes the bug. And since there are multiple ways in which you can patch a bug, therefore there can be multiple types of modifications or types of patches that you can generate or a repair technique can generate. So at a very high level, there are two classes or two categories of repair techniques. The first technique is called generate and validate, and it uses search-based software engineering to find code snippet which is similar to the buggy code and generate a patch. This class of techniques works on what is called as plastic surgery hypothesis, which states that it is often the case that the fix of a bug resides in the same or similar program somewhere else. And you can easily see that in your own experience. Like many times we do silly mistakes where we have written a correct code somewhere else in our program, but we forgot to, let's say, do I++, or we added instead of doing less than, we added less than equal to, and those kinds of things, right? So the assumption that these techniques work on is that the patch of a given bug exists in the program, and what these techniques do is they try to identify what are the similar code snippets which are likely to be correct and are similar to the buggy code snippet. And then these techniques try to replace the buggy code snippet with a similar code snippet, renaming variables and making sure that the code compiles, and then validating it against the test suite to see if the modified code passes all the tests. So that's called validation. So generate and validate. The next type or the next class of techniques is called synthesis-based techniques. These techniques, instead of trying to identify a similar code element and then modifying it in the buggy context, what they try to do is they try to synthesize the patch. Now, how do they do that? They first build formal constraints, for example, SMT constraints, which can be solved automatically using solvers, constraint solvers such as D3. I encourage you to look more by yourself about formal constraints and solvers. So I'm sure you might have heard of SAT solvers, for example. So these kinds of techniques build constraints from the test suite and then use those solvers to determine whether it is possible to satisfy the constraints under a given condition or under the given constraints that a buggy program is written. And if it is possible, it tries to generate or modify the buggy program itself to generate a patch out of it. So I'm not going to go deep into the techniques and describe, but like most of the techniques fall under these. So I encourage you to learn more about this, and I'll share the resources with you if you are interested, or write to me. Okay. Coming back to the repair process, third step of the program repair process is patch validation. Now that's the interesting part. Given a candidate patch which is generated by modifying the buggy code, the patch validation step involves applying that patch to the buggy code, or in other words, making the modifications to the buggy code, and then testing the patched program against the test suite and verifying if it passes all the tests. Now again, this is a very simple step in which you are initially given a test suite, you came up with a patch, and then you test whether your modified code passes all the tests or not, right? When you're doing this manually, when you are doing the manual bug fixing, it is very easy to assume that the modifications that you did yourself are correct because the tests are passing. But then this creates a huge problem when we switch to the automated program repair process. This assumption is no longer valid. And this relates to a very interesting thing called the Cobra Effect. I'm not sure how many of you have heard about it. So, a Cobra Effect is defined as when an attempted solution to a problem makes the problem worse as a type of unintended consequence. So here is a quick story for you guys. So in India, in probably very old days, there occurred a problem where there were a lot of wild cobras in the city. And the government announced that whoever is gonna catch the cobra and kill it or bring it to them, then they'll get a reward for that. So initially what happened was like people started hunting cobras and then they would bring them to whatever the wildlife people were there, and then they would get a reward for doing that. But then eventually what happened was like people kind of made this as their earning, and they started breeding more cobras in the cities. Uh, and the government realized that their scheme of getting rid of the cobras was not working because people are coming up with the cobras all the time. And then the government actually stopped that program, so now people will no longer get reward if they bring cobras. And this ended up having the repercussions of this was like now the city had more cobras than it initially had. So that's why it's called the Cobra Effect, because the solution of rewarding people was to get rid of the cobras, then it ended up in actually having more cobras. Now, how is this related to the program repair? Or what has this to do with program repair? So in program repair also, there's something similar has turned up. When we are doing manual program repair, we can rely the way we modify the program, and if our modification results in passing all the tests, then we say that yes, our fix is correct. But in case of automatic program repair technique, something interesting happens. Let's see. So here is a simple example. So here's a function Java code that finds the median of three distinct numbers. So the input are the three numbers A, B, and C, and the function is a median, and it checks the middle number between A, B, and C. So for example, the first if condition checks if B is the middle number. So here it is checking if A is less than B and B is less than C, or if C is less than B and B is less than A, then it should return B, and so on and so forth. Now here are some tests that are used to test this program, and there are a couple of tests that fail. Now I would like you to pause your video for a minute and see if you can spot the bug in the code. Also, it would be interesting for you guys if you could record the time it took for you to spot the bug. Okay, so I'm sure you must have guessed it right. So the bug is in this if condition where we are checking for A, but instead of doing B less than A and A less than C, the developer ended up making a mistake where he or she did C less than A, because of which these tests failed. So if you were to fix this bug, the correct patch that you would do or come up with is you would update the condition, and which would result in all of these tests to pass. There's a possibility that if you try to use automatic program repair technique to fix this bug, it might come up with something similar to the patch that I've shown here at the bottom, which will again pass all the tests, but is definitely not the correct patch. So again, I would ask you guys to pause your video for a minute here. Try to see if these two solutions result in passing all the tests, and what is the problem in this incorrect or overfitted patch. So why do you think it is an incorrect or overfitted patch, and can you come up with a counter example or a counter test case that could have prevented the repair technique to generate this patch in the first place? So here is one example of the test that will fail when you use this patch that is generated by a repair technique versus the one that you come up with. Okay, so what's the problem? So the problem here is that A repair technique is asked to find a modification that will pass all the tailing tests and will also pass all the passing tests basically, so it doesn't break the functionality that is already correct. And a repair technique is able to come up with a valid patch that is able to do what you have asked it to do. Now, how do a repair technique know that the patch that is generated is not correct or it is not acceptable to you? Isn't it? It's hard. Also, it is hard for human beings, for us, to manually evaluate these automatically generated patches and verify if they are correct or not, isn't it? So that's why it's a Cobra Effect. And so now you have solved a problem where you can generate a patch which passes all the tests, but still it doesn't quite solve the problem because you may end up breaking more functionality than actually fixing it if you just rely on the automatically generated patches. Another important hurdle in using this technology at the present moment is that manually inspecting these patches will not scale. Like repair techniques can generate hundreds or thousands of patches, plausible patches. So by plausible patches, I mean the patches that pass all the test suites but may not be correct. And unless you have a domain knowledge or domain expertise of the program, you won't be able to say whether a given modification or a given patch is correct or not, right? So therefore, it's a very, very big problem that prevents these program repair techniques to be actually used in practice. And that is the reason why most of the repair techniques that have been invented are not actually used in practice. Does that mean like there's no hope? So that's not true. People are constantly working on this and trying to make these repair techniques better such that they generate high quality patches. So when I say high quality, it means correct patch or which is acceptable to the developer and not the plausible patch. Alright. So now just reinforcing the thing that I just said, how do we evaluate the patch correctness? So one way is you manually view the patch correctness, and which requires you a domain expertise which will not scale, and you might be biased if you are the developer of the repair technique to probably say that the patch is correct, right? So an alternative way, which is an automated way and is a reproducible way to evaluate the patch correctness or the quality, is to automatically generate high quality evaluation test suites and measure the patch quality or correctness using them. Where the patch quality is a simple formula of how many tests are passed by the patched version of the program given the total number of tests. So what I mean by that is, for example, in this case, if suppose we had a separate test suite which had more tests and these tests are not given as input to the program repair technique. So for example, in this case, test number 7 was not the part of the original test suite. And now test number 7 is part of an evaluation test suite which you use to identify the correctness of the patch. So you can use that evaluation test suite to determine the correctness or quality of the patches. Now it is possible that you might end up making a incorrect patch as correct because the test cases that you come up with are again not complete. So it's possible that the modification that is done by an incorrect patch or overfitted patch also satisfies evaluation test suite, in which case incorrect patch might end up getting annotated as correct. But the reverse is never going to happen. So you will never discard a correct patch which is generated by the repair technique to be annotated as incorrect. Now, if you were doing it manually, you might, because let's say if you don't understand what modification is being done, then you might not be able to say whether the patch is correct or not, and then probably you will mark it as incorrect. So to solve this manual analysis and inspection problem, we have this alternate approach which we came up with in our lab, and here we use automatically generated high quality evaluation test suites. Now what do I mean by high quality evaluation test suites? So I'm not sure if this concept is covered in your class. So there's something called as code coverage ratio. What that means is when you execute a single test, let's say test 1, so how many lines of the code are executed when you execute test 1? So the fraction of the lines that get executed by a test upon the total number of lines is the code coverage ratio for that test. So similarly, you can have a code coverage ratio for the whole test suite, which checks what fraction of the source code statements get executed when you run the entire test suite. Now, if a test suite does not cover most of the source code, let's say the code coverage ratio of a test suite is less than 50%, then it is very likely that the program repair technique generated patch may pass all the evaluation test suite because you are not testing the whole code. On the other hand, if you have an evaluation test suite that executes most of the statements of your code, then it is very less likely that an incorrect patch that is generated by a program repair technique may pass all the tests of the evaluation test suites. So by high quality evaluation test suites, their quality is measured in terms of the code coverage ratio, or the fraction of the statements that are executed by the test suites. So now the question here is, okay, if we can use high quality evaluation test suites to measure the patch quality or correctness, so these evaluation test suites are basically not given as input to the program repair techniques. How do we get these evaluation test suites? So fortunately there are a lot of techniques. Again, test generation is an active research area in which people are currently working on, and there are some mature techniques that can be used to generate tests, which can be used as an evaluation test suites. I'm not going to go deeper into the test generation part, but then please feel free to ask me if you're interested, and then we can discuss this more. Okay, so in one of the research projects, what we did was we took 357 defects from 5 large open source Java projects. We took 4 repair tools which are popularly used and are very mature, and they seem to give good results. And we call this framework jarfly. So it's publicly available at jarfly.cs.umass.edu. Please feel free to look at it. Using this framework, what we did was we tried to patch these 357 defects using these 4 tools, and we try to evaluate the quality of the patches that are produced by these repair techniques. So here are the research questions that we asked in this study. So the first research question is, do generate and validate techniques produce patches for real-world Java defects? Now here we are focusing, in this study we focused on generate and validate techniques only. We did a separate study for synthesis-based techniques, and I'll share the results of that with you as well. Okay, coming back here, so the answer to this question was yes, although less often than C defects. So we found that when we try to patch 357 defects from these 5 projects using these 4 techniques, these techniques are able to patch around 11 to 19% of the defects. So 10.644 and 19% for syntax. And the plots show you how, like for each of the 5 projects or programs, how many bugs are patched by each of the techniques. Now, in a separate study, it was shown that generate and validate techniques were able to patch around 50% of the defects in a defect data set. So in this study, we found that program repair techniques struggle in fixing more Java defects. The second research question that we asked in this study is, how often and how much do the patches produced by the repair techniques overfit to the developer written test suite and fail to generalize to the evaluation test suite? So again, this is something similar to the patch quality we were talking about. So for the bugs that these techniques are able to patch, we generated evaluation test suites and we measured the quality of the patches that are produced by these techniques. And the answer to this question was, it's often. So it was found that only 13.8 or 14% and 46% of the patches pass 100% of the evaluation test suites. That means more than 50% of the patches that are generated by these techniques fail on the evaluation test suite. So that shows how current state-of-the-art repair techniques do. So we also did a separate study on the quality of synthesis-based repair technique, and in this study we came up with a new program repair technique called SOS repair, which comes from its earlier version of search repair that seemed to be generating very high quality patches for almost 97% of the programs. But then when we try to devise a SOS repair to work on real world large programs, so search repair used to work on very small student written programs like 10 to 20 lines, but SOS repair is capable of running on large real world C programs. So when we try to use SOS repair to fix the bugs in a defect benchmark called many bugs, we found that SOS repair was able to patch around 34% of the bugs. So this is of the order of the way Java repair techniques are working. And again, 41% of the patches that it produced passed all independent tests or evaluation tests. An interesting observation that was made in the study was, if we manually improve the fall localization, so we found that many times the incorrect patch was generated because the fall localization technique identified wrong faulty location. So if we correct the fall localization, and tell the technique, okay, here are the buggy elements, the technique was able to generate more correct patches. It was able to generate more patches, so now 35%, and 70% of these pass all the evaluation test suites. So the jump from 41 to 70% was huge. So this shows that fall localization itself could be an area which is kind of holding down the program repair technique's performance in terms of the quality of the patches or the correctness of the patches that are produced, right? Okay, so now the million-dollar question is, how can we improve the quality of the repair techniques? So when I say quality of the repair techniques, I mean the quality of the patches that are produced by the repair techniques. Now in the subsequent slides, I'm going to describe a very high-level ideas that we are working on. So this is an open research problem on which researchers are working everywhere around the world. So one of the idea is, can we improve fall localization? So as I told you in one of the studies, we found that for localization was actually an inhibiting factor, and if we improved it manually, we saw a huge jump in the quality of repair technique. Also, it's known that none of these for localization techniques is the best technique, and program repair techniques typically use spectrum-based. So the idea is, can we use alternative for localization techniques or maybe combine these multiple techniques? So recently there are some papers that are trying to use IR-based for localization techniques through the fixing and so on and so forth. So this is one way in which the quality of repair techniques could improve. The second idea is improve the patch generation. Now, patch generation is the core algorithm of the technique, right? So it is specific to the kind of technique, whether it's generate or validate or whether it's synthesis based. Now there are certain hybrid of these where you use both, so it's a little bit complicated. But here are some of the ideas in which you can also improve these algorithms in general. So the ideas that I'm specifying here are applicable to all the techniques. So first is like you can target specific class of defects. For example, instead of trying to fix all kinds of bugs, you can limit yourself in terms of fixing specific kinds of bugs, such as fixing only if conditionals or fixing null pointer exceptions and so on and so forth. So there are certain techniques that work only for specific class of bugs, and that reduces your search space, which helps you to improve upon the precision or generating more good quality patterns. Second is to use learned fixed patterns instead of hard-coded ones. So currently, many techniques, they try to use a fixed set of mutations or modifications. So by that, what I mean is they either try to add new code or replace the existing code with another code or delete some code. So these three are, for example, mutation operators. There are other mutation operators that have been used, for example, off by one errors, where you try to increase or decrease a counter by one, and then like checking the null pointer exception. So wherever you're trying to access, let's say array or some list, you check if it is not null and things like that. But these are all hard-coded patterns that are obtained by manually analyzing the kind of bugs that human developers make. But then we could also use some learned fixed patterns using modern machine learning techniques. And again, this is an active research area and people are working on it. The third idea could be to use novel search strategies and produce the correct patch first. This is another important problem in the repair techniques, that they are able to generate correct patches, but it turns out that the incorrect patch gets generated first and the process of the repair stops. So how can we make the repair techniques to generate the correct patches first and make the incorrect patches get generated later? The fourth thing is to use novel test sampling strategies to test candidate patches on the sample of test suite and reduce comparison. So another important aspect of the repair technique is that it uses huge computation resources, and executing the whole test suite for each candidate is very expensive. So can we use some strategies to optimize this such that the repair process doesn't stop because of the timeout? Okay, so we want the repair techniques to run only the tests that are relevant to the generated candidate patch, and then quickly identify if the candidate patch is valid or not, instead of running the whole test suite for each candidate. And finally, there are ideas in which we can use information from other software artifacts, such as contracts, specifications, bug reports, software code comments, in which repair techniques can, instead of using only the test suite as a specification, they can use these additional resources to judge whether a potential candidate patch is correct or not. So all these are the ideas that are applicable to improving the patch generation process. And finally, the third is to improve patch validation. So how can we improve patch validation? So as I told you before, one way is we can have better test suite such that it covers the code fully and makes sure that no incorrect patch will pass all the tests. Now this is very difficult to create such a test suite because you can always come up with some corner case that developers often tend to miss. So something that we came up with in our lab was to use natural language processing techniques to generate executable tests from natural language software artifacts. So for example, we try to make the existing developer-written tests better by generating more tests from the software specifications or like code comments and adding all those tests to the developer-written tests such that it improves the quality of the developer tests and prevents the techniques to generate patches that could potentially overfit. So again, this work is available as a free and open source tool, and it's available at swami.cs.umass.edu, and yeah, feel free to look at it. Okay, so to summarize, in this talk, I described to you the three-step process of automatic program repair, and I described to you different techniques for fault localization, for patch generation, and a possible way to do patch validation. Next, I described to you the patch overfitting or repair quality is a real concern, and I showed to you that more than 50% of the patches that are produced by the repair techniques overfit to the test suites which are given as input to the repair technique. Next, I described to you different ideas in which we can improve the quality of the repair techniques specifically by improving fault localization, patch generation, and patch validation. And for the latest updated research in the program repair research area, you can visit this website, which is constantly updated with the latest publication, tools, and benchmarks. For questions, you can email me directly at my email nmotwani@cs.umass.edu, or you can post it on Piazza. Either is fine. Okay, and then with this, I would conclude this talk. I hope you guys learned something and then it was useful for you. Hope to hear some questions. Bye, enjoy, and stay safe.